Perfect. So let's define. We have been talking about things like lists, sets, and then operation of sets, intersection, difference, union, and then we have talked about how we can use some defined functions already stored in gap file. And we can use this filtered function, number function, then we can use also the print function, and these are the functions like first of for all, collected, sum, the variant sum, the product. All these we can use like this, and we can combine different operations, different things like a bit of programming, and we can do that into the list. So instead of defining this list L and then calling like filtering it, we can just say filtered the list, and filtered what are we going to filter it, or how we are going to filter it. We can use also the collected command. There is now some basic programming. So this is the code we have done, and then this can give this kind of output. Okay, now let's try to do something with the polynomials. Okay, polynomials. Now, what do we need is to create a polynomial, we need to create the variable first, right? So let's define the variable. X is the variable, which is x of what? Rationals slash x. Okay, now we know that x is the rational number. Now, if we wanted, we could define several different variables this way. Now we can do all the usual arithmetic with polynomials. So let's say f is a polynomial. It is the power of x power 7 plus 3 into x plus 3 into x cubed, x power 6 actually, plus 5, x power 5 plus 3 into x square, or x power 3 minus 4 into x square and minus 4x. Okay, perfect. Now this is going to give me the polynomial. There is another polynomial. Let's say we have this polynomial, this g. Okay, now what can we do? F plus g. That's going to be adding all the terms, and then like f star g is going to multiply these two polynomials. F minus g is going to subtract these polynomials. Okay, the sum operations for integers hold for polynomials, like you can say quotient, remainder, your quotient, the table. There is quotient, remainder, command in here. And then if you just go f comma g, if you press the tab button, then it will give you the options for the functions. So this is the quotient and remainders. Okay, in the function you can also do mod. You can divide. You can do f mod g, and that will compute the remainder for you. And you can also do GCD of between these polynomials. I need to close it. So yeah, and that's the GCD between them. You can do GCD representation also. So GCD representation of FG, F comma G, right? So that's the GCD representation. That's how we represent the GCD. Okay. And then you can also do representation 1 star F plus representation 2 star G. You can also find the factors. Factors. You can also find the factors of the polynomial. Let's say first for F, these are the factors. You can also go for G. These are the factors of F and G. And then let's say F star G. Okay, these are the combined factors for F star G. Perfect. You can also, we have defined vectors and matrices before. You can also, now we can talk about the roots of unity. So the roots of unity, okay. Now the expression E of n is used to denote the nth root of unity. So, so that's how e power n 2 pi iota over n. So that is what I'm saying. So e power 2 star pi iota quotient n. Okay. And so you can do is root 5, fifth root of unity, and there that will be given as e of 5 minus e of 5 square minus e of 5 cube plus e of 5 over 4. Okay. Let's say we have that, and now we have root 5 square is going to be 5. Okay, and right, we can also define some finite fields and gap. So if you want to so say the finite fields, then we have to do something like this. Let me yeah, so the problem was that I have to put a share. So the finite fields to compute in the finite fields, we have to create a special objects to represent residue classes internally. Cape uses so-called ZEC logarithm and represent all non-zero num elements as powers of generators of cyclic multiplicative groups. So that means what we are talking about that, let's say GF is some variable which denotes GF7. That's the finite field. That's the finite group of order 7. And now one GF would give us the identity of this one. Right. And let's say we have an element A, which is 6 star 1 GF. So that is the Z7 power 3. Let's say we have another element B, which is 3 star 1GF. And that is itself Z of 7. And if we add Z A plus B, then we can just say that's something else. Let's talk about the integer of A plus B. That is just going to be 2. Okay. Now, non-prime finite fields are created in the same way with prime powers. Note that gap automatically represents elements in the smallest field possible. So you can, with the elements command for anything, you can actually call for the elements. And then these GF fields are already defined. You just have to call them like this. And then elements, there is S missing. And these are the elements inside Z16, you can say. We can also form matrices over finite fields. And that is, let's say we have a matrix which takes the values, which is the first row, which is 1, 2, 3. The second row is 5, 6, 7. Third row is 9, 10, 12. And we are multiplying 1 of IM. Wait a second, what is IM? Let's say that matrix. I think I have missed IM, defining IM. So let's say we just have 1 of GF. And now this is going to be a matrix inside the field 7. Field 7. Okay, perfect. Those are the powers for the matrix. Perfect. We can also, we can also do something like mat power -1 inverse of the matrix plus the matrix itself. And that would be this one. Perfect. We can also do integers modulo. So if you want to compute the integers modulo n, what we call Zn in the lecture, without need to always type mod, we can create objects that immediately reduce their modulo, arithmetic modulo n. So let's say IM is the integers mod 6. And this represents what? This represents numbers for modulo 6. Modulo 6 calculations. Integers mod 6. Okay. Now to convert ordinary integers to residue classes, we have to multiply them with the one of these residue classes. The command int converts back to the ordinary integers. Okay. So let's say A, convert an integer to the residue classes, you have to multiply with 1. So let's say 5 star 1 of IM. Now IM is defined. Okay, that is Z mod Zn objects which are 5, 6. Similarly, what can we do is, let's say we have B, which is 1 of 3 multiply 1 image, that is 3, 6. Now, if we add these two, that is 2, 6. But like if we do int of the last thing we have done, and that would give me 2. The integer in there is just 2. If one wants, one can get all residue classes, or for example, test which are invertible. So you can say call elements of M, okay? And that will give you all the elements, right? So you can filter them with the command lost. Lost are the elements. So you can say elements of M, maybe that works. X and is unit X. Yeah, so these are the units. 1 and 5 are element 1 and 5 have inverses. Okay. And you can also find the length of the last command, that is 2. Or you can say you can give the function length here, and then you can just check how many numbers have, how many elements have length, sorry, have inverse in the group 1 Z mod 6. Now, if we calculate modulo a prime, the default output looks a bit different. The default output would be that if we say M is the integers mod 7, and it will be just the field Z7. So the GF name is for the Galois field. Also, elements display differently, therefore it is convenient to once issue the command. Now we can also do matrices and polynomials modulo prime. So like as previously, you can also do a matrices and polynomials modulo prime that we did shown before. So we can use this command now because we have defined imp now. I am now. We can use this command that will give us the matrix like this. You can actually display the matrix if you want to see the elements, exact elements inside it. And those are these elements. Okay. And then you can also display something like the inverse of the matrix plus the matrix itself. And those will be these elements. In the same way, we can also work with polynomials modulo number. For this one, just needs to determine a suitable variable. For example, suppose we want to work with polynomials modulo 2. So let's define the variable R, which is integers mod 2. That will be the function field Z2. Now we define the variable X, which is X of R comma X. Now this means X is coming from Z2, right? Now F would be the function, which is X square plus X plus 1. Okay. Now that is what? That is this polynomial. We can vectors Factors of this polynomial will be themselves, because you cannot factorize this polynomial in the field Z2. S2 is a prime, and therefore every non-zero remainder invertible. We can now work with polynomials modulo f. The possible remainders now are all polynomials of a strictly smaller degree with coefficients suitably reduced. Okay, so let's say we have O, which is the identity of R. Okay, now we define L's as the elements with 0, 0 star x, 0 star x plus O, x, and then x plus O, not 0, O. Okay, these are the elements. These will be the elements now. We can now build addition and multiplication table for these four objects modulo f. Okay, so display, as you can see, if I'm using the display command, I can actually see the elements as numbers, not the symbols. So I'll use the display command and I'll give the list and a goes to list and b goes to position of AMS A plus B mod F. That will give me this matrix. So what I have done is that I introduced a list and take the list ALMS, which does that it sends every element of the list ALMS to the list which takes the list ALMS and sends every element of the list ALMS to the position of ALMS, adding the elements of the list A and B and doing mod F. That will be this matrix. Similarly, I can just do and then multiply these two list elements. And I'll get this matrix. Okay, now we can do groups and homomorphisms. Perfect. So, but before that, that will be an introduction to the groups and homomorphisms. So let's try to do a little bit of those, and then we can do like the main parts of those later. So let's say we can write permutations in cycle form and multiply or invert them. I think this should be after I define the groups. So yeah, I will end here and then we will see those things later in the later sections. Thank you.